This section covers the control registers of the Coherency Manager. The Global Configuration Registers, referred to as GCR, are the system programmer's interface to the Coherency Manager. The location of these registers in the memory map is determined at core build time. The GCRs are used to set the address for the Global Interrupt Controller and the Cluster Power Controller. They can configure the non-coherent areas of memory to either real memory or I/O devices. They control the coherency of the default shared memory region. They control the handling and reporting of Coherency Manager errors and any other options of the Coherency Manager. The Global Control Registers are memory map registers located in the system's address space. The GCR space contains control and status registers for the entire coherent processing system cluster and for individual CPUs in the cluster. All registers in the global control block are 32 bits wide and should be accessed only by using 32-bit uncached loads or stores. Reads from unpopulated registers in the GCR space will return 0, and writes are silently dropped without generating any exceptions. The GCR space has a total size of 32K bytes, which is divided into 8K blocks. The first block is the Global Control Block. This is a system-wide block that covers all global aspects of the coherent processing system. Some configuration values are on a per-core basis, so each core has a set of registers that pertain to these local configuration items. This set of registers is called the Core Local Control Block. The address range for this block is the same for all cores relative to the local core performing the load or store to this block. A core can access another core's local control registers by using the Core Other Control Block. That way, one core can read the status or change the configuration of another core. The address range for this block is also the same for all cores relative to the local core performing the load or store to this register. The selection for which core's registers will be accessed in this block will be covered later. The Global Debug Block is a system-wide block. It's used for debug purposes and performance information. The debug block will be covered in an upcoming section. The memory mapped address for the base of the global configuration registers can be found by reading CP0 Register 15 Select 3. Here are the macros that will allow you to access the register from a C program, and here is an example of calling that macro from C. The first register in the Global Control Block section is the Global Configuration Register. This register is a read-only register that gives you information on the configuration of the Coherency Manager in your system. NumAddr regions is the number of address regions. This tells you how many regions you could configure to support different coherency policies. You will use regions, for example, to configure an area of memory to be used for memory mapped I/O, or to change the coherency of a region between the L2 cache controller and real memory. I'll talk more about regions later in this section. NumIOCU is the total number of I/O control units in the system. P-cores tells you the number of cores in the coherent processing system. The GCR base register lets you configure the GCR base address and the coherency attributes under certain conditions. In most cases, this value is a read-only value, having been configured as an IP option when the core was built. Continuing with the GCR base register, the CCA override value and the CCA override enable are used in conjunction with the CM default target memory region shown in the next slide. As you will understand when I explain CM regions, you can configure each one with a starting address and size. The default target region covers any memory not already configured by a CM region. If you don't have any configurable regions, then this default region will cover all of memory. The CM default target can be set to two different types of addresses: addresses that go to memory and addresses that go to the I/O coherency unit for memory mapped I/O. Of course, if you don't have any other regions in your system, this default region should be set to memory. In a typical system, you would use the other regions to map to the I/O-CU type for memory mapped I/O, and this default region to map to a memory type. The CCA default override value controls the cache coherency algorithm between the L2 cache and memory. So if this is set to a write through, any writes to the L2 cache will also be written to memory. If it's set to uncache, writes will not be stored in the L2 cache and go directly to memory. If it's set to write back, all writes will be stored in the cache and only be written to memory if evicted or flushed. Last, if set to uncached, accelerated, writes will not be stored in the L2 cache, but will be gathered in a cache line size buffer before being written to memory. The CCA default override enable bit controls the enabling of the default CCA default override value. If this bit is set, the region will use the CCA default override value. If it is 0, it will use the same CCA as the L1 cache. The CM default target controls if the region is used for memory or memory mapped I/O. On bringing up your system, CP0 can control access to the GCR registers by other CPUs through the use of this field. Each bit represents a processor or a VPE in an MT system. Setting the corresponding bit to 1 enables writes to the GCR from that processor. The GCR revision register is useful when reporting issues to MIPS Technologies. The Coherency Manager can detect an individual request to the GCR, the Global Interrupt Controller, or the Memory Management I/O Controller. These invalid requests are usually caused by trying to access these controllers through something other than uncached accesses. It can also detect an invalid intervention request due to inconsistent L1 cache states caused by an improper coherence domain switch or an inconsistent cache attributes between two CPUs for the same cache line. The GIC has several registers. These are used to communicate error conditions, which I'll cover in detail in upcoming slides. All errors can be configured to cause an interrupt using the CM error mask register. There are 8 types of errors. Types 1 and 2 are global control register write or read errors that are caused by trying to access the GCR or the GIC register space in some other way than with an uncached address, like with the CCA of 2 causing a read of more than one word. Types 3 and 4 are coherent write or read errors that are caused by trying to access the GCR or GIC or MMIO with a coherent memory request. Types 5 and 6 are memory mapped I/O read or write errors that are caused by an I/O device trying to write to a memory mapped I/O space. This could happen if the I/O device is accessing itself or another I/O device by using the Coherency Manager. Type 17 and 18 are intervention read or write errors that can happen if software didn't follow the proper procedures for going into or out of the coherence domain. For example, if the data cache was not flushed when going from non-coherent to coherent, then it's possible for different cores to have incompatible states for the same line. Also, the cores could have different mappings for the same line, and this could lead to an error if one core mapped a line as coherent and another mapped it as non-coherent. Each bit in the GCR Global CM Mask register enables an interrupt for the corresponding interrupt type. The default interrupt mask is set to interrupt on write request and intervention errors. The interrupt asserts the SICM error signal. It is recommended that this signal be connected to the SICM init 0 of the GIC. The GIC section of this course will go into how the GIC is set up to do that. If the bit is 0, the error will signal a bus error exception for a data access. The next slide tells you how to break it down to the exact error. For either a bus error exception or an interrupt, the Global CM Error Cause Register will give you more information on the error. This register must be cleared after the exception or interrupt is handled. One of the 8 error types given in a previous slide will be set to the CM error type field. The CM error info gives you information on the error formatted based on the error type. The tables in the next slides will show you how to map the errors. There are 2 formats for the CM error info. Here's the format for the CM error types 1 through 5. And here is the meaning of the OCP M command. Here are the CM error info values for error types 16 through 31. Here's the encoding for the coherent state errors, and here's the encoding for the intervention response errors. Here are the encodings for the L2 error information. Here are the codes for the actions that caused the L2 error. The CM error address register contains the addresses which caused the error. It should be cleared after the exception or interrupt has been handled. The Global CM Error Multiple Register gives the type of error if a second error is detected before the first one is handled. It must be cleared after the exception or interrupt has been handled. The CM2 provides the capability of including custom user-defined GCRs. The GGU_EX bit indicates if the custom GCR registers exist or not. The new GCR custom base register sets the physical address of the base address of a 64K byte slice of memory space where the requests are directed to for the custom GCRs. The GGUEN enables the redirection of the memory request to the custom GCR memory registers instead of memory. The GIC is configured into the system at IP build time. The chip designer can decide to include the GIC or not. The GIC was configured into the system if the GIC EX bit is set. The CM2 adds the ability to issue a barrier sync to the L2 without executing a sync instruction, thus reducing the latency incurred for the sync. The L2 only sync provides a mechanism to guarantee that uncached requests do not pass previous cache requests in the L2 pipeline. For example, the L2 only sync can be used between an L2 hit write back cache op and a subsequent uncached write to ensure that the uncached write does not pass the write back from the L2. The CM2 only sync enable bit of the register must be set to 1 for this feature to be enabled. The address match is performed on a 4K boundary. An uncached write request address bits 12 through 31 that match the address bits 12 through 31 of the GCR L2 only sync base will cause the CM2 to treat the uncached write request as an L2 only sync. The Global Interrupt Control base address register is dependent on the GIC EX bit being set in the Global Interrupt Controller status register shown in the previous slide. Only if it is set is the Global Interrupt Control base address register valid. This register does two things. It's used to set the address of the GIC and to enable the GIC. The address is system dependent. You should consult your system specification or system designer to determine what address in your memory map the GIC is located at. That address must be on a 128K boundary. In other words, the lower 17 bits of the address must be zeros. This register should be written at system initialization time with the value of that address. In addition, the GIC enable bit controls the enabling of the GIC. Once the GIC has been programmed, this bit needs to be set to begin receiving interrupts. The L2 cache is configured into the system at IP build time. This register tells you if the L2 was configured into the system. If the major revision number is 0, there is no L2 cache. The cluster power controller is also configured into the system at IP build time. This register tells you if the CPC was configured into the system. If the CPC EX bit is not set, there is no cluster power controller. The I/O coherency unit is also configured at IP build time. This register tells you if the IOCU was configured into the system. If the major revision field is 0, then there is no IOCU. There are up to 4 programmable address regions that can be programmed to support memory mapped I/O or memory storage regions. A region that is mapped to memory storage can be configured to have a different CCA for the L2 to OCP interface than the L1 to L2 interface. Reads and write requests to a region that has been mapped to the IOCU go directly to the IOCU as non-coherent and uncached transactions. Each region is defined by a pair of GCR registers, a base address register and an address mask register that determines its size. The next slides will cover the configuration of these regions using these registers. This table shows you the offsets into the GCR where the region registers are. You program the region's physical address by writing to the region's CM base address register. Since the CM base address regions must start at a 64K boundary, only addresses with the lower 16 bits set to 0 are valid. The lower 16 bits will always read back as zeros. The CM region address mask determines the size of the region. The requested address is logically ANDed with the value of this register. The value of the associated base address register is also ANDed with the value of this register. If both outputs match, then the request is routed to the CM region. Only contiguous values are allowed. In other words, zeros between ones is not allowed in the mask. Continuing with the address mask register, the CCA override value and the CCA override enable are used in conjunction with the CM region target memory region. If the CAA override enable is not set, then the CCA for the L2 to memory is the same as the CCA from the L1 caches to the L2. If the CCA override enable bit is set, then the CCA value in the CCA override value field will be used for the CCA from the L2 to memory. The CM region target field directs the region to memory or the I/O coherency unit. The next two blocks in the control address space are the core local and the core other blocks. These blocks are local to a specific CPU. The core local block can be accessed at offset hex 2000 from the GCR base address. Using this address, all CPUs will see their own local set due to the magic of hardware. Hardware knows what CPU the address is being requested from, and it directs the request to the correct core local block. The core other block can be accessed at offset hex 4000 from the GCR base address. This block gives any CPU a way of accessing another CPU's CM local registers. To do this, the CPU writes to its own core other address register. I'll cover this in a bit. There are 5 registers in the core blocks. I will cover each in turn in the slides that follow. The core local coherence control register sets up the coherent domain for the CPU using the coherent domain enable field. This field consists of 8 bits, with each bit corresponding to a CPU on a single threaded system or a VPE on an MT system. Setting a bit enables interventions from the corresponding CPU. The bit that corresponds to the local CPU enables the coherence mode for the local CPU. This register is used by the local CPU to enter the coherence domain and to exit the coherence domain. The CPU needs to follow the entering a domain sequence, initializing the caches, enabling interventions from other cores, and enabling coherence mode for itself at reset and power up of the CPU. Before a power down of the CPU needs to follow the exiting domain sequence of disabling interventions, flushing its cache, invalidating its caches, and disabling coherence mode. The CM core config register is a read-only register that gives you information about the CPU. The first field, the IOCU type, will be set to 0 because a CPU is not an IOCU. The second field, the PVPE, will give the number of virtual processing elements in an MT system. If this is a single processor system, this field will be set to 0. If this is a multi-threaded system, the number of VPEs in the core will be the number of this field plus 1. The core number field of the core other address register needs to be written with the number of the other cores whose local registers you wish to access. Once this is written, you can access that CPU's CM local registers through the core other register block. The boot exception base field in the core local reset exception base register controls where the CPU will fetch the first instruction when it is powered up and reset. If you want to have CPUs that use different boot code, you could access this register through the core other group from another CPU and set the boot address for this CPU. The core local identification register is a read-only register that tells the CPU which CPU it is. The code will use this number to set up things like enabling coherency in the core local coherency control register. This register is an extension to the core local reset exception base register. The value is used for placing the exception base registers within the virtual address map during the core boot time. This will be covered in detail in the segmentation and EVA section. There are 9 thread context ID registers, one for each possible thread. The 2 bits of the priority value is passed with the memory transactions to the OCP bus. This enables the system to identify the TC that is associated with the bus transaction. This ends the CM register section.